In 1959, a physicist stood up in front of a room full of scientists and said something that made half of them laugh. He said we could write the entire Encyclopedia Britannica on the head of a pin. He said we could build machines so small they would fit inside a human cell. He said we could store every book ever written in something the size of a speck of dust. Nobody believed him. Some thought it was a joke. Some thought it was science fiction dressed up as physics. But the man saying it was not a science fiction writer. His name was Richard Feynman. And 60 years later, everything he described in that room became real. This is the story of the talk that predicted the future, before the future had a name. Stick around, because by the end of this video, you will understand why the smallest ideas in physics ended up building the biggest revolution in modern technology. Let's rewind. December 1959, the American Physical Society is holding its annual meeting at Caltech. Feynman is already famous in physics circles for his work on quantum electrodynamics, but he is not there to talk about that. He gives a talk called "There's Plenty of Room at the Bottom." The title alone tells you something. Room at the bottom of what? At the bottom of scale, at the bottom of size itself. Feynman was not describing a new particle or a new equation. He was describing a direction nobody had seriously pointed a telescope at, except this telescope pointed inward toward the impossibly small. Here is the open loop. The question this video is going to answer: if Feynman described nanotechnology in 1959, complete with molecular machines, atomic scale writing, and miniaturized computers, why did it take until the 1980s and 1990s for anyone to build a single piece of it? What was missing? Was it the tools? Was it the ideas? Or was it something else entirely? Something about how humans think about scale that kept us blind to what was right in front of us? Keep that question in your head. We're coming back to it. Let's set the scene properly, because context matters. In 1959, the biggest computers on Earth filled entire rooms. A single computer could weigh as much as a car and still do less math than the calculator app on your phone. Transistors were brand new. The idea of putting a machine inside a machine inside a machine, going smaller and smaller, was not something engineers were seriously pursuing, because the tools to see atoms, let alone move them, simply did not exist. Nobody had ever seen an individual atom with their own eyes. Feynman knew this. He knew he had no way to prove what he was about to say. He said it anyway because physics told him it was possible, and physics, to him, was the final word. Think about it like this. Imagine someone in 1959 telling you that one day you would carry a device in your pocket containing more computing power than every computer on Earth combined at the time. You would think they were insane. That is basically what Feynman did. Except he wasn't talking about computers directly. He was talking about something even stranger. He was talking about rearranging atoms one at a time, like moving individual grains of sand to build a sandcastle, except the sandcastle would be a machine, a circuit, a message, or a copy of a book. Here's a simple, real-life way to picture the scale problem he was solving. Picture a single grain of table salt. Now imagine that grain of salt is actually a warehouse, and inside that warehouse are millions of tiny rooms, each one the size of a single atom. Feynman's claim was that we could eventually walk into that warehouse, atom by atom, and rearrange the furniture, move this atom here, that atom there, and in doing so, build machines, store information, and eventually construct entire structures no bigger than a virus. To the scientists in that room in 1959, this sounded like fantasy. To Feynman, it was just an extension of physics doing what physics always does, following the rules to their logical conclusion, no matter how strange that conclusion sounds. Now here's the pattern interrupt, because I don't want this to feel like a history lecture. Let's talk about why this idea terrified some physicists at the time. And I mean that seriously. There is a concept in physics that says, as you shrink things down, the rules that govern them start to change. Gravity matters less. Something called van der Waals forces, the weak attraction between molecules, starts to matter more. Things get sticky in ways large objects never do. A tiny machine the size of a bacterium wouldn't fall the way a human falls. It would essentially float in molasses made of air. Feynman addressed this directly in his talk. He didn't ignore the weirdness. He leaned into it. He said, essentially, the laws of physics do not forbid this. They just require us to think completely differently about how small machines would behave. That distinction between something being impossible and something being merely unfamiliar is the entire engine of this story. Let's talk about the actual predictions, because they read like a checklist someone is completing 60 years later. Feynman proposed writing information at such a small scale that all the books in the world could fit in a space the size of a dust speck. Today we call this data density, and modern hard drives and DNA-based data storage systems are chasing exactly this goal, storing exabytes of information in spaces you could lose in your pocket. Feynman proposed building tiny machines that could build even tinier machines, a kind of atomic assembly line. Today we call this molecular manufacturing, and it is one of the foundational ideas behind modern nanofabrication. Feynman proposed manipulating individual atoms directly, moving them one at a time to construct materials from the ground up. In 1990, scientists at IBM did exactly that. They used a scanning tunneling microscope, a tool that did not exist in Feynman's time, to move 35 individual xenon atoms and spell out the letters IBM. It was the first time in human history that atoms were deliberately arranged to say something. It took 31 years after Feynman's talk for anyone to have the tools to prove he was right. That's the mid-video twist, the moment I promised you back at the open loop. The reason it took so long wasn't that Feynman was wrong about the physics. It's that the physics existed decades before the engineering caught up. He was describing something true using imagination, at a time when the actual instruments needed to test that imagination hadn't been invented yet. It's like someone in 1850 accurately describing how airplanes would fly using nothing but the laws of aerodynamics on paper, decades before anyone had an engine light enough to get off the ground. The idea was correct. The world just wasn't ready to build it. Let's bring this back to something you can feel, not just understand. Right now, the phone or screen you're watching this on almost certainly contains transistors smaller than what Feynman even dared to imagine in 1959. Modern computer chips pack billions of transistors into a space smaller than your fingernail, with individual components measured in nanometers. Distances so small that a single human hair is around 100,000 nanometers wide. Every time you unlock your phone, you're using technology built on the exact principle Feynman described at that conference. Go smaller. Keep going smaller. There is room at the bottom. Here's another pattern interrupt. A question worth sitting with. Why did Feynman, a man famous for quantum electrodynamics, care about something as seemingly unglamorous as atomic scale engineering? The answer says something about how great scientific minds actually think. Feynman wasn't interested in fame or in staying in his lane. He was interested in what physics allowed. Full stop. He once said that what one fool can understand, another fool can. Meaning, if the laws of physics permit something, nature has already built a proof of concept somewhere. And he was right. Biology had been doing nanotechnology for billions of years before Feynman ever gave that talk. Every cell in your body is a nanoscale factory. Ribosomes are literal molecular machines that read genetic code and assemble proteins atom group by atom group, 24 hours a day, without you ever noticing. Feynman wasn't inventing something alien to nature. He was pointing out that human engineering could, in principle, catch up to what biology had already perfected. This is the climax, the big reveal this video has been building toward. Feynman's 1959 talk wasn't really a prediction about gadgets or tiny robots. It was a prediction about a mental barrier, the assumption that human scale thinking is the only valid scale to build at. He was telling an entire room of scientists that the universe doesn't care about human intuition. It doesn't care that atoms feel too small to matter, or that molecular machines feel like science fiction. Physics doesn't forbid it, so eventually someone will build it. And they did. Nanotechnology today touches medicine, where nanoparticles deliver drugs directly to cancer cells without harming healthy tissue. It touches materials science, where nanoscale coatings make surfaces waterproof or self-cleaning. It touches computing, where every leap in chip performance over the last 30 years has been a direct descendant of the idea Feynman floated as almost a thought experiment. So here is the answer to the open loop I asked you to hold on to. Why did it take so long? Not because Feynman was ahead of physics, but because he was ahead of engineering, and engineering always takes longer to catch up to imagination than we expect. The lesson underneath this entire story is bigger than nanotechnology itself. The biggest breakthroughs often don't start in a lab with a working prototype. They start with someone standing in a room saying out loud the thing that sounds impossible, simply because the math says it isn't. Feynman didn't have a microscope that could see individual atoms. He had something more powerful. He had the confidence that if physics allows it, reality will eventually make room for it. If this video made you see your phone, your computer, or even the ground beneath your feet a little differently, that's the whole point of this channel. We take the ideas that changed how humanity understands reality and we make them make sense, without the jargon, without the gatekeeping. If you want more of this, hit subscribe, because there is a lot more room at the bottom of this channel too. Drop a comment and tell me what tiny idea you think will change the world next, because 60 years ago, almost nobody believed this one would.